Hello, and in this video we're going to go back to basics and look at fixed point numbers. Working with decimal places in our programs is something we take for granted these days. We've got hardware that can do dedicated floating point operations with high speed and great accuracy. But sometimes you just need to do these things by hand, and you'd be surprised how simple it can be. Before we can start investigating alternative storage formats for numbers, let's just do a little bit of revision on arithmetic with binary numbers. In decimal land, the number 531 is represented as 5 times 100s, 3 times tens, and 1 times units. And we add all of those together, which is no doubt 500 plus 30 plus 1 equals 531. Another way to look at this is that the 1 is multiplied by 10 to the power 0, the 3 is multiplied by 10 to the power 1, and the 5 is multiplied by 10 to the power 2. Units, tens and hundreds. Storing numbers in binary is no different, except instead of base 10 we use base 2, and we usually limit the number of bits. So in all of the examples today I'm going to limit myself to 4 bits because it's less for me to write. And so here I'll have 4 bits. And just so we're all talking the same language, this one is my least significant bit, and this is my most significant bit. And just as we did with 10 to the power of an index, we can do the same here. So this is the same as 2 to the power of 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. This means our most significant bit represents 8s, then 4s, then 2s, then 1s by our least significant bit. And that gives us a total, if we add them all together, of 15. Now, including 0, that means we've got a total of 16 states, which is unsurprising given that our 4 bits, if we do 2 to the power 4, equals 16. To convert a number from decimal to binary, we undertake a small algorithm. So let's assume I want to convert the number 7 in decimal to our binary equivalent. Well, the first thing we ask ourselves is how many 8s fit in a 7? Well, the answer is 0, and we'll carry that 7 over. How many 4s fit in a 7? Well, there's 1, but now we've got 3 to carry over. How many 2s fit in a 3? Well, it's 1, and now we've got 1 to carry over. How many 1s fit in a 1? Well, it's 1, and we've got 0 to carry over. We have completed our algorithm. And those familiar with binary will instantly recognize 0, 1, 1, 1 is 7. When we consider our state space of all 16 states to represent only unsigned numbers, we know that we can represent 0 through to 15. If we want to store negative numbers, we have to start interpreting the bytes as signed, which we artificially apply a range of -8 to +7. Let's assume now I wanted to represent -7 as a number. Well, I need to take the 2's complement of 7, and the 2's complement is quite an easy calculation. Firstly, we invert the bits, so 1, 0, 0, 0, and then we add 1, giving us 1, 0, 0, 1. Moving into the sign domain does make the numbers look less intuitive, but mathematically things begin to start working out. So if I take my 7 and add it to my -7, I should get 0 as the result. 1 plus 1 is 0, but carry a 1. 1 plus 0 and the carry is then again 0 and carry the 1. 1 plus 1 is 0 and carry the 1. 0 plus 1 plus 1 is 0, and there is no 1 to carry anymore. The final result is indeed 0, i.e. the maths checks out. And what this elegantly demonstrates is that by representing the 16 states of our 4 bits somewhat differently, we can add additional functionality. In this case, we've added the ability to have negative numbers. But the sacrifice we have made is we have halved the range. That's because we are still only limited to 16 possible states. Given that the interpretation of the states is somewhat arbitrary, there's nothing stopping us using those states to represent a number between 0 and 1. Since I know that I have 16 possible states, if I wanted to map those states onto the range 0 to 1, then each state must be representative of 1/16. And this 1/16 is the smallest possible resolution that I can use to represent the number in that range. Programmers like numbers like 16 because when you see them you immediately think of 8 and 4 and 2 and 32 and basically powers of 2. Let's just make a rudimentary number line, and at this end I'm going to represent 0 and this end I'm going to represent 1. And just as before I'm going to use 4 bits to represent fractional powers of 2. Now I know that 1/16 is my least significant bit, therefore it makes sense that 1/8 would be next, then 1/4, and my most significant bit would represent a half. Surprise, surprise, laid out on our number line, this is all split up nice and evenly. Halves, quarters, eighths and sixteenths. Remember, we can only represent a number in the space 0 to 1 that is a multiple of our lowest resolution, in this case 1/16. So let's suppose we wanted to represent this number, 13/16. We can see that this consists of 1/2 plus 1/4 plus no eighths, but plus 1/16. In regular binary, this is 8 plus 4 plus 1. It's 13. That makes sense. But if we interpret it differently as 13/16, we've got a decimal representation. How would we represent something a little bit more tricky? Let's assume, for example, the value 0.1. Well, if we follow the algorithm that we did before, we would ask ourselves how many halves fit into 0.1. The answer would be 0, and we would carry over the 0.1. How many quarters fit into 0.1? 0, and we'd carry over the 0.1. How many eighths fit into 0.1? Well, the answer is still 0. And how many sixteenths fit into 0.1? Well, the answer is 1. And just to make this a bit clearer, I'm just going to put the decimal equivalents here. 0.5, 0.25, 0.125, and 0.0625. So what we have said here is that by applying the same algorithm as before, we have approximated 0.1 to being 0.0625. Well, that gives us an error of 0.0375. Intuitively, however, I would look at this and say, well, surely the 0.125 is a better approximation. And indeed, if I did use the 0.125, then my error becomes 0.025, which is smaller. This means we can't just use exactly the same algorithm as before. When we're performing decimal to binary conversion, we're using integer divisions, which truncate and round down. So we are biasing our algorithm to underestimating the values. We can fix this by taking the value we're trying to convert and bias it in favor of being rounded up. So now when we perform the conversion, we get 0010, which yields a more accurate result. What's even nicer is this biasing trick is consistent. If the number we wanted to represent was 0.4613, we would still bias it by forcing it to round up at the end. Since we now have 4 bits representing 16 states on the right-hand side of a decimal point, and we know that the numeric values of these will be half, 1/4, 1/8, and 1/16. This also corresponds to 2 to the power minus 1, 2 to the power minus 2, minus 3, and minus 4. On the left-hand side of the decimal point, we can represent the whole number, which we know is 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3, giving us 1, 2, 4, and 8. We've got 16 possible states on both sides of our decimal point. So for every state on this side, there are 16 possible states on this side, which means we've got 256 possible states, and as we know, if we represent all 8 bits, we have 256 possible states. So this is reassuring that we're using the entire state space to represent a decimal number, where we have 4 bits on the left-hand side and 4 bits on the right-hand side of the decimal point. And this is fundamentally what a fixed point number is. So let's do a couple of little tests. Let's start by representing the number 7.5. Well, we know that on the left-hand side, the 7 is represented now as 0, 1, 1, 1, And the 0.5 on the right hand side, don't forget we bias it upwards by making it really 0.55. How many halves go into 0.55? Well, 1. We carry over the 0.05. How many quarters go into 0.05? None. How many eighths go into 0.05? None. How many sixteenths go into 0.05? None. I'll just turn that 6 to a 16. And so we can see quite clearly here in binary, in this fixed point notation, the 7 and the 0.5. Let's add in another number, 2.1. So in this case, in binary, we know it's 0, 0, 1, 0, decimal point, and we've just done 0.1, taking into account the error, which was 0, 0, 1, 0. The nice thing about fixed point notation, and it just goes to show that binary representations are a very abstract entity, is we can add them in exactly the same way we would have added two 8-bit integers. So here I know that the answer is 9.6. But let's add these in binary, starting from the least significant bit. 0 and 0 is 0, 0 and 1 is 1, 0 and 0 is 0, 1, decimal point. 1. 1 and 1 is 0 with a carry, 1 and 1 is 0 with a carry, and 0 and 1 gives us 8 plus 1, which is 9, and on this side we've got half plus an eighth, which is 625. That's not a bad approximation at all. And what's really cool is we've added these two 8-bit numbers, and it really didn't matter whether the decimal point was there or not. The adding hardware just treated them like regular 8-bit numbers. It's purely the way we have interpreted the result that we can see it actually represents a decimal point number. The same applies if we move to signed space as well. Instead of 7.5 plus 2.1, I'm going to do 7.5 subtract 2.1, which is the same as doing 7.5 plus negative 2.1. So I want to take the 2's complement of this number. I'm going to forget for a minute that it's in fixed point notation and just take the 2's complement of the 8 bits. So recall that I start by inverting the bits and then I add 1 to them. 1 plus 1 is 0, carry a 1. 0 plus 1 is just 1. Nothing to carry, nothing to carry, nothing to carry. 1 plus 0 is nothing to carry. 0 plus 0 is nothing, nothing to carry, and nothing to carry. Now I need to add the 2 together. So 0 plus 0, 0. 0 plus 1, 1. 1. 1 plus 1 is 0 with a carry. 1 plus 1 plus 1 is 1 with a carry. 1 plus 1 is 0 with a carry. 1 plus 1 plus 1 is 1 with a carry. And finally 1 plus 1 is 0, and we have a carry going out somewhere into the wilderness. If we now look at what we've got here, we've got a 4 plus a 1, which is 5. And here we've got a quarter plus an eighth, which would give us 375. So our final result is 5.375. Does that check out? Well, the actual answer is 5.4, which is not bad at all. And so again, another demonstration that just using conventional integer hardware, we're more than capable of approximating decimal numbers. And this is really cool. We're using just 8 bits and we've got decimal numbers and signed decimal numbers at that. If I had two 8-bit numbers and multiplied them together, the worst case scenario is I would need 16 bits to store the result. The same applies when we're trying to calculate a fixed point multiplication using integer hardware. But of course our end result can't just occupy more bits. Fundamentally, we need to scale back down the result of the multiplication to suit our fixed point notation, and as a result we sacrifice some precision. Let's go back to decimal, and indeed let's go back to school by doing some long multiplication. Let's consider the calculation 3.5 times 2.25. So 0 times 5 is 0, 5 times 5 is 25, so it's 5 carry a 2, 3 times 5 is 15, plus the 2 is 17, stick the decimal point in. Then we insert a 0. 0 times 2 is 0, 5 times 2 is 10, carry a 1, 3 times 2 is 6, plus that 1 is 7. Then we insert 2 zeros. 0 times 2 is 0, 5 times 2 is 10, carry a 1, 3 times 2 is 6, plus that 1 is 7. And then we add all these together. 0, 5, decimal point, 7, 8, 7. And once we had the result, we had to rescale it. We counted the number of tens, so in this case it was tens and 100s, and we divide by that 100 to get our final result, which is effectively moving the decimal point backwards. 7.875. Here we counted how many powers of 10 did we move the decimal point by, and down here we divided by the same. When we move to our fixed point notation, so let's say our 4.4 fixed point notation, and multiplied those together, we do exactly the same algorithm to compute the result, but we must remember to divide by 2 to the number of bits representing our decimal. It's exactly the same. So to facilitate multiplication, we're using just the integer hardware as before and scaling back down into our fixed point notation. Division is a similar process, and I'm not going to subject you to long division on stream. I can't remember it myself. However, we'll see in the next section where we start to implement this in code that division does have a peculiarity about it, but it's all very familiar. And I'm starting with a blank Visual Studio solution, and I'm not including the Pixel Game Engine. Yes, this is not a Pixel Game Engine video today. To begin with, I'm going to create a fixed point type, which is 16.16. That means we've got 16 bits on one side and 16 bits on the other side of our decimal point. The reason I've chosen this is it very conveniently fits into the type int32t. So int32t's are going to be used to store our fixed point numbers, although mathematically the meaning of the number won't be the same. I'm going to create a little utility function that will conveniently convert a double precision number into our fixed point numbers for us. Now, the whole point of doing fixed point in the first place is you probably don't have floating point hardware availability. However, I'm going to assume that for the purposes of this video that you do, and this is really all just a bit of an educational exercise. So I'm going to make a function called double to fixed. I'm going to pass in the value of the double. And I want to play around with the number of bits after the decimal. So I'm going to turn this into a template function, where we specify as an argument the number of bits we want after the decimal point. To convert the double to our fixed point number format, I need to multiply it by 2 to the power of the number of bits we want after the decimal place. This will scale the double into the integer space. Now, I'm going to get nagged a lot about casting on here, so I'm going to be explicit, and it also helps cement the ideas that I'm trying to put across. And when we're doing this conversion, we mustn't forget that little hack to accommodate error. And the nice thing is, rather than trying to work out what the furthest digit away from the decimal point is and adding 0.000005 or whatever it is that needs to be, once we've scaled the decimal into our integer space, then we can just add or subtract 0.5 to it, and the rounding will take place accurately. Now I'm going to do something a little unusual for one lone coder. I'm going to start using const expression almost everywhere in this video, because it's interesting to let the compiler do some of these things at compile time rather than waiting for runtime, and we'll see how this pans out. Let's use this function to convert a double to our fixed point notation. Double to fixed. We're going to use 16 binary digits after the decimal place, and we'll pass in the number. Let's pass in 3.5. That's one of the ones we're experimenting with in the slides. Now, if I also make this variable const expression, IntelliSense will quite happily go away and calculate some of it for me. Now, I'll zoom in on the video, but it says here that the result is A equals 229376. Well, let's bang that into a calculator. In programmer mode, 229376. And if we move over to the binary version here, we know that the bottom 16 digits are on one side of the decimal and the remaining digits are on the left-hand side of the decimal. And this looks about right. Remember, 0.5 being the first, the most significant bit of our decimal part, and 3 being the least significant bit of our larger part of the fixed point number. That's very nice. We can actually see 3.5. So just to keep this sane, let's also make a function which converts our fixeds to doubles. That way we can display them. And this time I'm going to use Z to store the result of our fixed to double function, pass in how many bits we're interested in, and pass in the integer 32, which is our 16.16 representation. So all of this is now being done by the compiler rather than needing to run the program. If I put my cursor over Z, I see that the end result is 3.5, which is encouraging given that we're passing in 3.5 to begin with. And if I change this to minus 3.5, we don't sort of see any errors flare up, the end result is still minus 3.5. If I pass in 3.1, because we had interesting properties with 0.1, let's see what we get as a result here. We see minus 3.10000. There's whatever the minimum representation of 16 bits worth of decimal places are. So I'm guessing that's 1 over 65,536. Which is fine. Don't forget that when fixed point notation is always an approximation. So let's add some numbers together. Let's keep this nice and simple. 5.6. We'll just see what does that actually get approximated to. Well, it's not bad actually, 5.6 and a bunch of zeros afterwards. And we'll add in another one, which is B. And we'll say that this one is 2.7. And we'll add these together to give us the result C. A plus B. And we'll pass in C to our conversion function to look at the result. And the result is telling me it's 8.3, which is accurate. Let's do another one, but this time we'll do some subtraction. D is minus. We'll have a look at what the end result is there. 2.9. Again, that looks pretty good. Right, let's do some multiplication. Now, we can't just rely on the integer multiplication alone. Don't forget we need to do some shifting. So effectively we're using the integer multipliers to do long multiplication. So I'll take this as a starting point. We'll call it E. And it's going to be A times B. Now, we can't do this directly because we need to start working within a larger type. Therefore, before I do the multiplications, I'm going to cast these to a larger type. Twice as big, in fact. And then we scale the final result down by our 2 to the power 16. Let's have a look this time. So 5.6 multiplied by 2.7, 5.6 multiplied by 2.7 is 15.12, and the end result here is 15.119995. Not bad at all. And what's nice to note is we've done nothing but integer operations. Now, you'd be forgiven for thinking that divide was somewhat similar. Let's put in an F. But instead of shifting one way, we shift the other. Let's have a look at what the result should be first. So 5.6 divided by 2.7 is 2.074 recurring. Our result here is just simply 2. Well, it could be, but I feel that we've lost some accuracy. What we have here is effectively A divided by B multiplied by 2 to the 16. In this example, A and B are integers. And of course this is an integer divide, and integer divides throw out information. So here we have two similarly scaled integers, which we then divide, throwing out information, and then we scale back up. But given that division and multiplication have the same precedence, we could do this in a different order to give us a more accurate integer divide. We could change this to A multiplied by 2 to the power 16 divided by B. Now we have a very large integer A divided by an integer B, and the whole thing is already scaled, so we'll actually be losing less information during this integer divide. Let's test this theory. And so by taking advantage of that precedence, we can now see that the final result is 2.074. 0661, okay, fair enough, but actually it's reasonably accurate to, well, 4 decimal places. That's a really nice result. Now, with anything involving integers and division, we do need to be careful of integer divide by 0. So I think this is pretty neat. We're doing just integer operations, but we're calculating decimal mathematics. Let's test the theory by changing the nature of our word. Let's change it to 30 bits of precision before the decimal point and 2 afterwards. We just need to change our 16s to 2s in order for our system to be updated. Now, of course, only having 2 bits of decimal precision does limit things quite considerably. So let's have a quick look at what it thought our A value was. So 5.6, the best it could approximate it was 5.5. And if we look at our B value, the best it could approximate that was 2.75. So that's not too bad at all. If we have a look at our addition, the end result was 8.25. Should have been 8.3, but it's doing the best it can with what it's got, aren't we all? If we look at our subtraction, it's 2.75, which again is not far off. Our multiplication is 15 in this case, whereas it should have been 15.12. And finally, our division is just simply 2 in this instance, where it should have been 2.074 or something like that. So not bad at all. Very flexibly, we've managed to change the dynamics of our number system entirely. I think it's time to wrap all of this up in a nice little utility class. I'm going to create a class called fixed, and again it's a template class where we're going to pass in the argument which is the basic type. So this would be int32 in the example just shown, but we also need to pass in something that's twice as big, so int64 in this case, and again the number of bits that we want after the decimal point. And I don't intend to spend too long doing this because we've looked at the basics now, so it's just a case of operator overloading. I'm going to store in my class of the type value, which is the fundamental raw selection of bits that represent our fixed point word. And everything is going to be const expression again, so I'm going to give it a default constructor, and I'm going to give it a constructor which takes in a double and populates the raw bit value, just as we did before. I'm going to make it so you can cast our fixed class to a double by overriding the double cast operator, and this implements essentially our fixed to double function from earlier. And for reasons that will become apparent in a second, I'm just going to add in a small static private function which is used to form one of these objects by setting the bits directly, and that's just to make some syntax a little easier later. So let's start adding in some operator overloads. Firstly, we've got the assignment operator. Again, const expression, and all it's going to do is be the default. It'll just copy one value over to the other. Let's add in now an addition operator. So this calls that form function I mentioned earlier by taking in the two raw values and performing the integer addition. Naturally, if you've got an addition operator, you probably want the plus equals operator as well. It goes without saying that subtraction follows a very similar pattern indeed, except subtractions instead of additions. Now, there's an operator that people tend to forget to implement at first, and that is negation. So if we wanted to have a unary operator, in this instance, it just takes the raw value of the class and forms a new object with the inverted value of it. Multiplication is, well, just as you'd expect. It's the same as the multiply functions we've just implemented down here, except this time, rather than explicitly typing out the types, it's using it from the template. And again, division. So I don't have to keep repeatedly typing out the template specification, I'm going to use the using keywords to create a nice name called fixedpoint16_16, which represents a 16.16 fixed point number that we've been implementing earlier. As you can see, I'm passing in the 32-bit type, the 64-bit type, which is used for the working space, and how many positions of decimal place accuracy do I need. So let's create some numbers. As before, I'm going to create a variable a, which is 5.6, and another b, which is 2.7. And we'll have a look at our result again. We'll call it a double again. Z equals, now we mustn't forget to do the casting, a plus b. So 5.6 plus 2.7, our z is calculating that as 8.3. There you go, very nice. And because we've overloaded the operators in a way you might expect, of course the other operators work just as well too. But now we've got even more flexibility. We can, for example, change our basic type. So let's go now to having 8-bit decimal numbers. So we need 8 bits for our main type, 16 bits for our working space, and we're going to have 4 bits of decimal precision. And we'll call this one an FP44. And we'll just change these over. And we can see that's functioning too. Remember, this should have been 15.12. It's now coming out at 15.0625. It's the best it can manage. Now that we've got a working library, we could start to build more sophisticated functions. For example, let's do something that calculates the circumference of a circle. The circumference of a circle is of course 2 pi r, but we need the 2 and the pi to be in our fixed point format. So we could do it like this: 2.0 times fp 3.14159, get it as accurate as we can, times our radius. I'm just going to pick a to be our radius in this case. And we'll get the final result in our z value. So circ gets calculated to be something, and it's saying that our 2 pi r is 35.125. Let's go and bang that into a calculator. So it's 2 times pi times 5.6 equals 35.186-ish. So it's not done so bad. And of course, if we change all of these to give it more precision, it's going to give us a better result. We can perhaps improve upon this with a bit of syntactic sugar. And we can use one of the newer features in C++ where we can create our own literal suffixes by overriding the operator. In this case, it's a string literal operator, and we'll create one called _fp44. And all this does is take in a double as the argument and creates a fixed point number to our 4.4 specification. And it means we can get rid of this, and we can just simply go 2.0 fp44 and 3.149 fp44. I really dislike that. But the compiler is more than happy to go ahead and calculate the result for me. And so that's that. Now I am sure there are fixed point number aficionados out there that can poke holes all the way through this and find all of the strange edge cases where we're not looking after error properly. That said, I still believe there's a lot of value to understanding what's going on behind the scenes using fixed point numbers. It's worth doing the binary by hand occasionally, and even for those that have been doing this for years, a bit of a refresher is not a bad thing. Anyway, if you've enjoyed this video, give me a thumbs up please. Have a think about subscribing. I'm going to throw the code on the Discord so you can steal it for your homework, and I'll see you next time. Take care.